Now, the restoring moment which comes due to the buoyancy force is given by m restoring is again Sk sin theta into Vk into rho w g. Okay. Sum this up for k equals 1 to n, where n is the number of submerged elements and Vk is the volume of kth element, rho w density of sea water, and g is acceleration due to gravity, which is 9.81 meter per second square. So, I call this as equation number 4. In fact, I rewrite equation number 4 straight in a different form as restoring moment is rho w g sin theta summation k equals 1 to n s k v k. I call this as equation 4. Okay. Now, I have the overturning moment, which is m overturning. I have the restoring moment, which is m r. Okay. Now, I can always find the resistive moment. Which is otherwise called as recentering moment. If you recollect, it is important to note that compliant structures are generally designed to have a very high recentering capability. Therefore, let us try to find out the recentering moment, which is given as R t, which will be actually equal to the restoring moment minus overturning moment. The restoring moment minus overturning moment, if I call this as R t from a original equation of motion, please look at the original equation of motion. From the original equation of motion, this is my restoring force. Okay. So, this should be equal to my restoring force, in fact restoring moment, because I am taking moment about the hinge in all the cases. So, I should say this should be actually equal to k of 1 plus r of t into theta. So, now I substituting. So, this is going to be equation 5. Now, substituting from equation 3 and equation 4 in equation 5, we get sin theta rho w g summation k equals 1 to n of s k v k minus sin theta summation k equals 1 to n s k w k is actually equal to k 1 plus r t of theta. So, I call now this as equation 5 after substitution, let us say 5a. Now, for small rotations, that is theta being very very small, sin theta can be said as theta. Then when the tower is in undisplaced position, k will be equal to, because now in the above equation theta will get cancelled. Let us write down the equation for more clarity. So, I should say rho w g summation k equals 1 to n skvk minus summation, there is theta here, summation k equals 1 skwk theta is equal to k of 1 plus t theta. So, for small values of theta I write the equation. Now, theta gets cancelled, okay, and in undisplaced position you will see that this value will also be set to 0. So, now k will be actually equal to rho wg summation of k equals 1 to n 0 skvk minus summation k equals 1 to n skwk. Now, you may introduce a new term which is n 0, let us say where n 0 is total number of segments when the tower is undisplaced. Okay. So, at any instant of time gamma t can be computed as R t by k theta minus 1, equation 7. So, gentlemen, please look at equation 6, which is this equation. It gives me k, okay. Equation 7 gives me R of t. Please note that R of t depends on both theta and n at any instant of time. Hence, it is displacement dependent. Let us talk about mass moment of inertia of the tower about the base. So, which is equal to I t, which can be summation of k equals 1 to n w k by g s k square, because mass moment of inertia about the base. Okay. So, second moment of area. So, plus rho w summation k equals 1 to n 0 C m minus 1, that is variable submergence s k square into V k. So, that g is divided here. Okay. So, rho w g, so it is g here. Now, if you look at the equation of motion, that value should be actually equal to the inertia component. This is the inertia component. Okay. So, now this actually should be equal to the inertia component, which is 1 I 0 1 plus B t. I call this as equation number 8. Now, for undisplaced position of the tower, mass moment of inertia is given by I 0 equals summation k equals 1 to n s k square w k by g plus rho w summation k equals 1 n 0 C m minus 1 s k square V k. This is equation number 9. So, let us equate equation number 8 and 9. Okay. So, equating equations 8 and 9, we get I t by I naught minus 1 will be B t. So, friends, look at this equation. We wanted I 0, B t, k and gamma t to qualify the complete equation of motion. So, we got, let us say, k from equation 6, then I t equation 8, beta t equation 9 and gamma t from earlier equation in equation 7. Okay. So, now we have obtained all variables I, beta t, k, gamma t, which are necessary to form the equation of motion. Okay. We have got this. So, let us talk about f of t, moment of the forces about the base, that is about the hinge. Okay. So, f of t will have two parts. The first part will be exposed portion above water will be subjected to wind load, submerged portion which is underwater will be subjected to wave load at any instant of time. Okay. Having said this, the hydrodynamic force per unit length at two nodes, let us consider two nodes, node I and I plus 1, okay, of element j. So, f I of t will be half rho w c d d j u dot n I minus theta dot h I absolute u dot n I minus theta dot h I plus pi d j square by 4 C m rho w u double dot n I. Let us call this equation number 11. Let us find out the force for I plus 1th node of the jth element. So, half rho w c d d g u dot n I plus 1 minus theta dot h I plus 1 absolute u dot n I plus 1 minus theta dot h I plus 1 plus pi d j square by 4 C m rho w u double dot n I plus 1. I call equation number 12, where h I is the height of the ith node above the base, d j is the dia of the jth element, u dot n plus 1 u double dot n plus 1 or velocity and acceleration of the water particle at node I. Thus, moment of the jth element caused by wave load is computed. Total force will be obtained by summing up all the forces acting on all elements about the base. Now, since f of t, beta of t and gamma of t are dependent on displacement theta, the solution to this equation of motion is iterative. We have already discussed the numerical method for solving an iterative solution. We can use either Newmark's beta method, which is one of the direct integration procedure to solve the problem. The computer method for solving this problem, the computer code is already available to you. You can alternately solve this problem using iterative frequency domain method, which is relatively new concept in solving equation of motion of this type. Okay. So, friends, in this lecture we learned one application problem on articulated tower. We already have a computer program which calculates omega and phi for the known value of mass and k. So, for mass and k to be input, one can find out omega and phi. So, this example explained you how to find out mass, which is as same as I naught, and k for this problem. Once you know mass and k, one can compute C using the computer code. The problem also helped you how to estimate the wave forces, which is f of t for a given tower using finite element. Since the solution is iterative, we already know how to apply Newmark's method to solve this problem. So, one can easily write a computer code algorithm to solve this problem and try to find the vector theta with the help of computer codes given in part and parcel. Thank you very much.